Now let's examine the mean value theorem. Notice this time there's only two criteria. The first two criteria, the only two criteria, being the same as the first two of Rolle's theorem. The function must be continuous on the closed interval from a to b. The function must be differentiable on the open interval from a to b. Notice though the third criteria that the y values are the same, the endpoints are the same y value, is not there. So if these two things are true, then there must exist at least one number c in the interval a to b where f prime of c, the derivative, equals f of b minus f of a over b minus a. So the derivative at some x value equals the average rate of change. Think about what that means graphically. Derivative means slope of the tangent line. But when I do this, this is also slope. It's just a slope over an interval given 2 points. And a slope of a line that goes through 2 points is the secant line. So thinking of this graphically, what mean value theorem tells us is that there will have to exist at least one location on the graph where the tangent line has the same slope, parallel means the same slope, as the secant line. So the tangent line and the secant line are parallel. Also, the instantaneous rate of change, remember instantaneous rate of change is the slope at one point, also known as the derivative, right, equals the average rate of change, or the slope over an interval, or given 2 points, which is our slope formula from up here. Not the derivative, but the change in y over the change in x using our 2 points. I'm going to draw a function that satisfies Rolle's theorem. So remember what that means. I make it smooth and curvy, I start at one point, and I end at the same point, at the same level. Y values are the same, smooth and curvy, never pick up my pencil, end at the same levels. Connecting the endpoints with a line, so from here to here, what's the slope of that line that I just connected? Yep, the slope is 0. Well, remember what Rolle's theorem says? We can find at least one place on the function that has a tangent line where the slope is 0, somewhere the derivative is 0. So connecting the endpoints, I have a slope of 0 because from that y value to that y value, it's horizontal. And there's at least one place, possibly more, on the function where the tangent line is horizontal. Well, now I'm going to draw a function that satisfies only the first two parts of Rolle's theorem, the first two parts of the criteria. So that means the endpoints don't have to be at the same level. So for example, I can start here and I can curve somewhere, but then end up, I don't know, maybe about here. That's not so pretty. Let's try that again. And end up right here. So I'm not at the same y value where I started. I'm going to connect the endpoints with a line like I did here. So from this point to this point, I'm going to pull this out so that I can draw it a little bit straighter. So from here, and I might need to rotate that, and I'm just using this to get a nice straight edge. Okay, so one point to the other. There we go, I connected it. Connect the endpoints with a line, estimate the slope of that line. Well, I'm on graph paper, so I don't have to estimate. I can literally count down 1 over 1, 2, down 2 over 1, 2, 3, 4. So down 1 over 2 is my simplified slope. So let's write my slope is negative 1/2. Is there anywhere else on this function where I can draw a tangent line that has the same slope? Well, I'm going to take my ruler, which is at that slope, and just keep sliding it, sliding it, sliding it, sliding it, sliding it, and there you go. There it is right there. I can draw a tangent line right there, has the exact same slope. That's mean value theorem. Mean value theorem tells us that no matter where those two endpoints are, there has to be at least one place on the function where the tangent line has the same slope as the secant line. Remember, connecting the endpoints, that's called the secant line. At one point, that's called the tangent line. The tangent line has the same slope as the secant line. What is the slope at a tangent line called? The derivative. So here, the derivative is -1/2. What is the slope of a secant line? Well, if this is at A and this is at B, the slope of the secant line is f of B minus f of A over B minus A. Change in y over change in x. So what we are saying is that it doesn't matter if the two endpoints have the same y value. If the function is continuous and differentiable, then the slope of the secant line will equal the slope of the tangent line at least one place in the function. Derivative equals the average rate of change. Determine whether the mean value theorem can be applied. Now, just like Rolle's, we have criteria, but here we have less to worry about, only two parts. So first, is this function continuous on this interval? Well, I see there's a discontinuity because there's a denominator. It equals 0 when x equals 0, and that is on this interval. So, number one has failed. G of x is not continuous at x equals 0. So we can say it's not continuous on the interval -1 to 1. Therefore, I don't have to look any further. Therefore, the mean value theorem does not apply. Can't go further. If so, find the value of c that satisfies the conclusion of the theorem. If not, explain why not. We did that. We're done with this one. Let's look at the second one. Same exact function, same exact, but notice I changed the interval. So now I'm looking at 1/2 to 1. Well, the function's still discontinuous, but at x equals 0, it's not on that interval. So looking through the three criteria, 1, g of x is continuous on our closed interval. 2, we know these rational functions are smooth and curvy everywhere, so also it's differentiable on the open interval. And that's it. Therefore, mean value theorem applies. And we know that means that there's at least one place where the derivative equals the average rate of change, and we can find that place. So at least one place where this happens. If so, find the value of c that satisfies the conclusion. So let's do that. We need the derivative. Let's make ourselves a little bit more space here. Finding the derivative. So g prime of x, we have a quotient, but it doesn't have to be a quotient. Simplifying that, x over x plus 1 over x, 1 plus x to the -1. So the derivative of that is 0 plus -1 x to the -2, or -1 over x squared. So our derivative, this guy. Now our average rate of change. So using our interval 1/2 to 1, we're going to do g of 1 minus g of 1/2 over 1 minus 1/2. So plug 1 in. Okay, so we're doing this part right here. Plug 1 in there. 1 plus 1 is 2 over 1 is 1, so that's 1. Minus 1/2 plus 1 is 3/2 over 1/2. Oops, and I just realized that's not 1. That's 2. 1 plus 1, so that's 2. Minus, and plugging in the 1/2, that's going to be 3 over 1/2. So 2 minus 3 is -1 over 1/2 makes -2. So that's going to be -2. So we're saying that the derivative has to equal the average rate of change. So our derivative has to equal our average rate of change. So let's set them equal. Negative 1 over x squared equals negative 2. I'm out of space a little bit here, so I'm just going to move over to where I have some more space, solve that equation. Negative 1 over x squared equals negative 2. Looks like x squared equals 1/2, so x equals plus or minus the square root of 1/2, but only one of those is on my interval, the positive 1. So c equals the square root of 1/2. Free response from an AP exam, let's see what they say. F is the function given by this. Find the number C that satisfies the conclusion of the mean value theorem. So they're implying that the mean value theorem applies. They're not asking us to check that it applies. So all we have to do is, what's the conclusion? The derivative equals the average rate of change. The derivative is 3x squared minus 7. And the average rate of change is plugging in 3, plugging in 1 over 3 minus 1. Plugging in 3, plugging in 1, that makes 12 minus 0 over 2, or 6. So continuing down on this side, we're looking for where 3x squared minus 7 equals 6. Let's solve from there. X squared equals 13 halves, or x equals positive or negative the square root of 13 halves. Wait, 13 halves? Oops, nope, 3. 13 thirds. 13 thirds, square root of 13 thirds, but only on 1 to 3. C is the square root of 13 thirds. This is a little bit more realistic of a situation. Two stationary patrol cars equipped with radar are 4 miles apart on a highway. As a car passes the first patrol car, its speed is clocked at 55 miles per hour. 3 minutes later, when the car passes the second patrol car, its speed is clocked at 50 miles per hour. So notice these numbers here. On a highway, typically 55 miles per hour or greater is the speed limit. So we might say that this car was not speeding. However, we need to prove that the car must have exceeded the speed limit of 55 miles per hour at some time during the 3 minutes. But 55, 50, it didn't exceed the speed limit. So how are we going to prove that it must have? Well, the two cars are 4 miles apart, and 3 minutes is how long it took for the car to pass from one of them to 4 miles later where the other one was. So how fast is its average speed? So normally we think of speed as miles per hour. How many miles did it go? 4 miles. And how many hours was it? Well, 3 minutes. That's minutes instead of hours, but I can find the hours by taking those 3 minutes and saying, well, in 1 hour, I would go 60 minutes. So multiplying by 1 over 60 or dividing by 60, I can find out that it's 1/20th of an hour. And 4 divided by 1/20th makes 80. Ouch. 80 miles per hour is this guy's average speed. He just slowed down a lot from the time he first saw the cop to the time he saw the second cop. Well, the velocity of his car, the speed of his car, is a continuous function. It's not going to jump over random blips of time. So since the velocity of the car, the speed of the car, is a continuous and differentiable function of time. There's no blips in time that are taking us from one point to the next. It's instantaneous rate of change, or velocity, because velocity is speed, has to equal its average rate of change, or to stay consistent with what we said here, average velocity, according to the mean value theorem. By mean value theorem, its instantaneous velocity must equal its average velocity. It's instantaneous. It's speed at any one point. It's speed at one point in time must equal its average velocity, which we calculated to be 80 miles per hour. So at one point, this guy had to be going at least 80 miles per hour. We proved the car exceeded the speed limit at some point in time. Let's look at another way to use mean value theorem. F is a function that's differentiable. Remember, when it's differentiable, that implies that it's continuous. Second derivative is greater than 0. Using the chart below, find a positive number r having the property that there must exist a value c on the interval and such that the second derivative at that point equals r. So thinking about the fact that it's differentiable, meaning it's continuous, we know that mean value theorem applies. So how can we use mean value theorem? So if we know that f prime of c has to be f of b minus f of a over b minus a, since mean value theorem applies, it works for any level of derivatives. So if we want to know f double prime of c, let's apply it to that. F double prime of c is f prime at b minus f prime at a over b minus a. Well, I have those values from the table if I plug in the values for my endpoints. 0 and 0.5. So instead of b, let's put 0.5. Instead of a, let's put 0. And let's evaluate that using our table. So looking up here at the table, f prime of 0.5. 0.5 is here. F prime is 3. So this is 3 minus. F prime of 0 is 0. So 3 minus 0 over 0.5 minus 0 is 0.5. 3 divided by a half is 6. So we know that f double prime of c has to equal 6 by mean value theorem. Therefore, r, the value we want, is 6.